We are still in Unit 9, and this is Day 4. This is Notes for Integration of Powers of Trig Functions. So again, let's take a look at where we've been this unit. So far, we've done several things, and now we're on Step 4, Integrals of Powers of Trig Functions. All right. So, to introduce this, I'd like to begin by taking a look at something that we've already done. We've already done some integrals of trig functions. So let's take a look at this integral, this antiderivative. Okay, the first thing I'd like to do is, so what would we do here? And I will tell you that for some reason, with trig functions, kids want to use some kind of a weird product rule on trig functions, on integrals of trig functions, and it just doesn't work. Okay, here's what they like to do. They like to say, oh, this is just the antiderivative of sine, which is negative cosine, times the antiderivative of cosine, which is sine. That was easy. I'll put a plus c and we're done. Well, that's just not true. It's just not true, because if we take the derivative of this, we do not get back that. So this is not true. So in general, if you have a product of two functions, I don't care if they're both trig or both algebraic or both some other transcendental, if you have a product of two functions in here, our integral is not the antiderivative of the first times the antiderivative of the second. It's not. That's not true. Okay? That would make things way, way easy, but it would also make them wrong. So that's just wrong. So don't do it. Okay? Don't do it. Another thing that kids like to do here, because we're doing these powers of trig functions, if we have, let's say, sine squared dx in here, for some reason kids like to say, oh, it's just a power, I can use the power rule. They see a power, they want to use the power rule. So they'll say, oh, that's sine cubed x, because I raised the power by 1, and then I just multiply by a third, add c, I'm done. Gosh, this was so easy. No, can't do that. It doesn't work. Because if we take the derivative of this, we do not get sine squared. If I took the derivative of this, let's come off to the side, and let's take the derivative of that. So, yes, there's a power of 3. I would multiply it by the coefficient. We'd get a 1. And then I would reduce the power by 1. And I'd get a sine squared. But then there's a little thing called the chain rule. And then we'd have to multiply by the derivative of sine x, which is cosine x. This is the derivative of 1/3 sine cubed x. And that is not what we have in our integrand. So you cannot just come and use some weird power rule. The power rule only works for x to the n power. Only works for that. And even then, n cannot be -1, right? But anyway, do not use the power rule on a function. It can only be an x, all right? So I say that because those are two common things I see for some reason in this particular section, okay? All right, on the notes page that I gave you, on your notes page, I have some things that will help you. Okay, first of all, keys to success with this. Know all of your basic trig derivatives and antiderivatives. Even the antiderivatives for the ones involving a natural log, right? These were the other ones that we learned, right? So know all of these. You just simply must know these. Okay? Choose a good U and use U sub. And then use your trig identities effectively. Those are the keys to success. Here are some trig identities that are particularly nice to know. Okay? The Pythagorean identities, we kind of know those. We've used those a lot. We have not used so much these double angle identities though. Okay? So these are helpful. Sometimes we use them going backwards. So sometimes we would have this because sine of 2x is easy to take the antiderivative of. This is hard to take the antiderivative of. So in that first example that I gave you, I would change that to a sine of 2x. It would be 1/2 sine of 2x. So sine of a number times x, cosine of a number times x, those are easy because we know all of those. We know all of those antiderivatives, right? All right. For cosine, we want it to get down to cosine of 2x, all right? So these are both really valuable ones to know. If we have a cosine squared x or a sine squared x, we'll change them to these. Okay? All right, let's take a look at some examples. Example 1. Let's say that we have the integral of cosine to the 6th of 3x times sine of 3x dx. Okay? So if we have this, I see a good U that we can make U be, and then we'll do a nice U sub. And I'm going to let U be cosine of 3x because du will have a sine of 3x in it. So let's take the derivative. We're taking the derivative. So the derivative of cosine 3x is negative 3 sine 3x dx. So in place of sine 3x dx, what are we putting in? We're putting in negative 1/3 du, right? Because we would bring that negative 3 over. So negative 1/3 du. So this becomes negative 1/3 integral u to the 6th du, bringing that negative 1/3 outside. Now go ahead and use your power rule. So when you do a u sub, you're getting something that we can use the power rule on mostly. So this would be 1/7 u to the 7th plus c. So we get negative 1 over 21 cosine to the 7th of 3x plus c. Example 2. What if we have sine squared of 5x dx? Well, as soon as I see that sine squared, I know I'm using this. Sine squared is 1/2 plus 1/2 cosine of 2x. This is a trig identity that you got to know. All right? So whenever I see a sine squared, I know I'm going to go and use that. Right? Now, so we have 1/2 plus 1/2 cosine of what? Well, sine squared of x has a cosine of 2x. Then sine squared of 5x is going to have a cosine of 10x. And now let's find the antiderivative. This will be 1/2 x plus, okay, the antiderivative of cosine is sine. Keep your argument. Then it's an antiderivative, so we have to undo that 10. It's the opposite of the derivative. So this is 1 over 20 plus c. Okay, example 3. The antiderivative of cosine squared of 4x dx. Well, as soon as I see that cosine squared by itself, I know I'm using cosine squared x is 1/2 plus 1/2 cosine of 2x. These two are really useful, you guys. Know those two. Okay. So I'm going to change this to the antiderivative of 1/2 plus 1/2 cosine of 8x. So we'll have 1/2 x plus 1/16 sine of 8x plus c. Example 4. The antiderivative of cotangent squared x divided by cosecant x dx. All right, for this one, now it's getting a little bit more challenging, right? A lot of times kids will say, ooh, I want to change this to sines and cosines right now. And that will probably, you could do that. You could probably do that. I see another thing that I can do that I would like to do first, okay? But I probably, we'll see. We'll see what happens. What I see is this cotangent squared x. I'd like to change that to something with tangent squared, or not tangent, cosecant squared. So I'm using the Pythagorean theorem, or the Pythagorean identity, that says cotangent squared x plus 1 is cosecant squared x. So in place of cotangent squared, I'm going to put cosecant squared x minus 1. Okay, you might be saying, why in the world did I do that? Well, now I've got two things up here, and now I can split them up into their pieces, which is always a good thing. So I have the integral of cosecant x, which I know the antiderivative of. I have that memorized. Minus 1 over cosecant x is just sine x. Now the antiderivative of cosecant x, you just need to know this, okay? Just need to know this. It's negative ln absolute value cosecant x plus cotangent x. I remember the one for secant x, and then I can get the one for cosecant x. But you just need to know those, all right? And then the antiderivative of negative sine x is positive cosine x plus c. Example 5. Integral of tangent x secant squared x dx. Well, I see two ways to do this problem, because I see this is a u sub. If I let u be tangent x, what is du? Secant squared x dx. If I let u be secant x, what is du? Secant x tangent x, which I would have left. I'm going to do this two ways, and I'm going to show you that they are equivalent to each other. So the first way, I'm going to do a u sub where u is tangent x. Du would be secant squared x dx, which is right here. So that would be my du. So I would just have the integral of u du, which is 1/2 u squared plus c. So that would be 1/2 tangent squared x plus c. Okay? Let's come over and do it the other way. To do it the other way, well, I will write this exactly the same. Okay? So to do it this way, I'm using u is equal to secant x. Then du is secant x tangent x dx, which I do have there. I'm going to use one of the secants for my u and the other secant for this secant in the secant tangent, right? So this would also be the integral of u du, which is 1/2 u squared plus c, which is 1/2 secant squared x plus c. Both of these answers are correct. Take a look at that. They're both correct. Does that mean that tangent is equal to secant? Is tangent x equal to secant x? No. So what's going on there? How can both of these be correct? Well, I know that secant squared x is equal to tangent squared x plus 1, right? That's a Pythagorean identity. So this is 1/2 tangent squared x plus 1/2 plus c. Now does it get better? Are these two c's necessarily the same c? No. 1/2 plus c is just another constant, isn't it? So now it makes more sense. So yes, these two can be correct. They are equivalent to each other because these two c's are not necessarily the same c. All right, number 6. The antiderivative of cosine cubed x sine cubed x dx. Now we're getting a little interesting, as if we weren't already. Okay. So in class we would probably take a little time and you guys would tell me what you think I should try here. Okay. We can't just do a plain u sub. If we let u be cosine, then du would have a sine in it, and we'd still have lots of the u cubed would be fine, but then we would have extra signs, right? Same thing if we let u be sine x. So that's not going to work. What would happen though if we left this cosine cubed x and we changed sine cubed x to sine squared times sine? Then in place of sine squared x, we're going to use the Pythagorean identity, because that is 1 minus cosine squared x. So I'm going to change this to cosine cubed x times 1 minus cosine squared x times sine x dx. And now this is going to be, I'm going to distribute, so this is going to be cosine cubed x minus cosine to the 5th x sine x dx. Now I'm liking it, because now I can do the u sub that I wanted to do earlier, because I just have a single sign over here that's going to be part of my du. So I'm going to let u be cosine x, du is negative sine x dx. So in place of this sine x dx, I'm putting a negative du, and then I have negative, I'm pulling that negative outside, u cubed minus u to the 5th du. So when you have something like this, pull out one of them. Pull out one of them and change the rest to your other function. And then you can do a u sub like this. So this is going to be a negative 1/4 u to the 4th minus 1/6 u to the 6th plus c. So this will be negative 1/4 cosine to the 4th x plus 1/6 cosine to the 6th x plus c. Now we could have done this using, instead of keeping a sign, we could have kept a cosine, and then our u would have been sine x rather than the cosine x here. In that case, our answer would be in sines rather than cosines. Okay? So you can have again, you can have equivalent answers like that. Okay. Example 7. Integral of secant to the 5th of 3x tangent 3x dx. Keep in mind that the derivative of secant is secant tangent, and the derivative of tangent is secant squared, right? Keep those in mind. We always know those. We have to know these really well, okay? So, if I let u right now be tangent, du would be secant squared, and I have too many secants to do that, okay? Right now. But, I might be able to break this down to where I have just a secant squared left, maybe? Or, if I let u be secant, then du would be secant tangent. Do I have a secant tangent that I can use here? I do, don't I? That's the thought process. So, that's the thought process. I'm going to break this up into secant to the 4th, and then I'll have a secant 3x tangent 3x to use for my du if I let u be secant of 3x. So u is secant of 3x. du then is 3 secant 3x tangent 3x dx. So in place of this, I'm putting in 1/3 du, right? Because we have to move that 3 over. So this becomes 1/3 integral u to the 4th du. And now it's just a power rule. So these are just, you're saving part of the trig function to use for your derivative. So this will be 1/3 times 1/5 u to the 5th plus c. This is 1/15 secant to the 5th 3x plus c. Kind of clever, huh? All right, number 8. Antiderivative of secant to the 4th x dx. This is one where kids want to just use the power rule on it, and you can't do that. We can only do power rule on x to the 4th, not secant x to the 4th. All right, what to do here? Well, you certainly can't do a u sub where u is secant, because there's definitely not a secant tangent to use for the du. So the only thing I can think of to do is kind of to split this up. Secant squared x times secant squared x. And now what? Well, again, I'm just like, what can we do here? The only thing I can think to do is use that Pythagorean identity that says that that is true. So I'm going to replace one of these secant squareds with tangent squared x plus 1. Okay? Why did that help me? Because now I see it. Now, if I let u be tangent x, du is right there. See secant squared x dx. Right? So this becomes the integral of u plus 1 du. All right, here's where I want you to be careful. The antiderivative of u du is 1/2 u squared. You guys, what's the antiderivative of 1 du? Kids tend to put an x right here, and it's not an x, it's a u. All right, so be careful with that. So we get 1/2 tangent squared x plus tangent x plus c. Remember that you can always check your answer by taking the derivative of this and getting back that. Okay? A couple more examples. Number 9. This is where I usually get a groan in the classroom when I say 2 more examples. Okay. Antiderivative of 1 over cosecant x cotangent x dx. Okay, what to do here? I'm not sure what to do here. So when I just don't know what to do, I will change it to sines and cosines and go from there. So that's what I would do here. So if I change this to sines and cosines, first of all, this does mean, it does mean 1 over cosecant x times 1 over cotangent x, right? That's what that means. So 1 over cosecant x is sine x, and then 1 over cotangent x is tangent x, which is sine x over cosine x, right? So we have here sine squared x over cosine x dx. Well, again, I kind of like that because for sine squared x, I tend to use that, well, in this case, if sine squared was by itself, I would use that identity with the 1/2, but it's not by itself. It has that cosine with it. So I'm going to use 1 minus cosine squared in for sine squared. Okay? That helps me because now I have 2 things in the numerator, and that's usually a better thing than having 1 complicated thing in the numerator. Now we do this guy. So this is integral 1 over cosine, which is secant, minus cosine, and now we know those antiderivatives. We know them. Antiderivative of secant is natural log absolute value, secant plus tangent. Antiderivative of cosine is sine, so this will be negative sine x plus c. Okay? There may be another way to do that problem, but that's the way that I saw to do it. Okay? There are lots of different ways to do these. There are not lots. There's usually more than one way to do these problems. Okay? Sometimes I do a longer way than what somebody else will do. And that's okay. Sometimes I do it shorter. So it's all good. Okay, example 10, last example. Antiderivative of cosine cubed 2x times the square root of sine of 2x dx. Okay, this looks very complicated, doesn't it? So when I take a look at this, I'm not sure what to do. I would like to let u be sine of 2x. That's what I want to be because it's underneath this radical. But then I have this cube on the cosine and it ruins it. So, but that's what my thought process is. I would sure like to let u be sine of 2x. Okay? Well, I can do that if I split this cosine cubed into cosine 2x times cosine squared 2x and then change the cosine squared 2x to sines using my Pythagorean identity. So that's my thought process here. I'm going to take a cosine out and save it for my derivative, because the derivative here will be 2 cosine of 2x, right? So that's going to be part of my du when I get there. All right, so now I'm going to keep this cosine 2x for my du. In place of cosine squared, I'm putting 1 minus sine squared. Okay, now I have all signs here, so now I can come and use this u sub that I wanted to use. So in place of this cosine of 2x dx, let me go grab that. In place of cosine 2x dx, we need to put 1/2 du, right? So we have 1/2 integral 1 minus u squared times u to the 1/2 du. Now we can do this because we can distribute that u to the 1/2 through the parentheses. This will be u to the 1/2 minus u to the, we're adding the exponent, so 2 plus 1/2, right, is 5/2 du. So we'll have u to the 3/2 times 2/3, and then over here we'll have u to the 7/2 times 2/7 plus c, right? These were the ones you remember way back that we factored things out of. Do you remember factoring things out of? We factored out like the common thing on the bottom. Anyway, this would be 1/3. U was our sine of 2x. So sine to the 3/2 x minus 1/7 sine to the 7/2 x plus c. Okay. Fun with trig functions. Love it. The more you do, the easier they seem. All right? The more you do, the easier it is to see what approach will work. All right? There's no way around it. You have got to practice these. So go practice.